Welcome to Chapter 1. In this video, I'm going to talk about the goal of the control and how the workflow in control looks like. So if you remember from Physics 101, there's a free-falling object with the gravitational acceleration, which is constant, and using this popular F equals ma equation, we can make that acceleration is equal to the gravitational acceleration on this body. And then we can eventually integrate this equation left and right hand side equally, and then we have velocity equation, and if we integrate this one more time, we're going to have position equation. So using these equations, we can answer the questions like, how long does it take for this ball until it hits the ground? Or when it hits the ground, what is the velocity of this free-falling object? And so on. Also, in this kind of situation, we can answer the questions like this. You're driving a car, and you see this traffic light changes to red, and you step on a brake with a constant deceleration, and then how long does it take for this car to stop? How long does it take, or how far does this car to take until it fully stops? In control engineering, however, it answers a little different questions. Let's assume there's an aggressive driver here, and this driver sees the traffic light changes to red. And then the driver wouldn't stop immediately, but instead it kind of keeps traveling further and then steps on the brake very aggressively right at there. Another case, if he's a little milder driver, the driver may step in on the brake immediately, but not aggressively, gently stepping on the brake and eventually stop there with a slower and longer distance. So these are the questions that the control engineering answers. So it's a little different perspective. In Physics 101, we assume the initial conditions such as velocity and position is fixed. And then the input force such as constant acceleration and deceleration is determined. And then we can just predict with this initial condition how the system will change. That's the Physics 101 question. In control, we know that we are going to stop or we are going to reach a certain position. But how are we going to reach there, like aggressively or peacefully? That's about the control answers. Also, as you can see from this image, well, just controlling position and velocity is not just one control task. There could be additional tasks, such as balancing this bike while you're moving through a straight line or curved line. Sometimes you might want to keep this angular position of this bike upright, but when you're curving, then you might want to tilt the bike a little bit. So keeping a certain state in a certain way, such as bike angular position, is not a control task. So how to control and what to control is something that we are interested in. One example about the balancing is this. This is a bit old research from AIR&H. The researchers made this cube with the reaction wheels. And as you can see, this cube can balance in a very impressive manner. Actually, this kind of reaction wheels is a basic mechanism for satellite attitude control. By the way, when I say attitude control, it's not altitude control. Satellite attitude control means controlling the angular position of the satellite. Actually, the word attitude is often used in aerospace when they control their aircraft and satellite and so on. That was a side note. And another control task could be something like this. So in this video, I'm controlling this drone with this joystick. So what I'm trying to test is that as I move this joystick, how fast this drone behaves. And as you can see, this is not the best controller because of the significant delay. So to solve this issue, well, there are two ways. One way is simply train the pilot better, harder, faster, so that the person can handle the delay of the system, or simply make the controller better. So these are the control tasks in general, like what to control, how to control, and to test, does it follow your input? Now, let's see how the control workflow looks like. In a very high level, we can talk about maybe 5 steps in general about the workflow in control. The first thing we might do is drawing the free body diagram using a pen and a paper. Next, using the differential equation, which is just a language to describe a system or picture, we can write a differential equation or a set of differential equations. What I'm talking about is a very simple thing like this. Literally draw free-falling ball and this force, which is the gravitational force. And then describe this system using a language of math or differential equation. And you can just write a simple equation like this, A equals G. And to solve this differential equation, you can integrate this and so on. But we're going to talk about this detail later on. So after describing this differential equation, describing the free body diagram with differential equation, we can convert this differential equation into a workable form of the differential equation, because differential equation itself is just a description about the system. So we cannot really do too much about this. So we have to change the form to, for example, a transfer function or state space matrix. And then using this workable form, we can design finally the controller. And after the design, we can implement. However, the implement is a kind of murky term. In reality, implement may mean literally assembling the hardware or making this circuit and wire them correctly so that eventually you can control the motor like this. And eventually you can code up the controller that you have designed previously onto a microcontroller. However, what's most likely to happen is that you may need to go back to the very first step. Regardless of you intended it or not, you may realize that you're missing some terms or differential equation itself is wrong and so on. One very simple example could be like this. You describe this system, free-falling object with the differential equation, but sometimes you realize you're missing some terms. At least on this planet Earth, there's an air. We need to take into account the air resistance, for example. So that thing is the actual sort of issues that always comes up in the daily life. Also, even if you didn't miss anything, but still, the differential equation may not perfectly describe your actual system. And that's because the measurement problem. For instance, let's say we are measuring a length of a pencil. It's about, say, 5 centimeters. However, the 5 centimeters is not a perfect information because we are not really going down to the atom level and then count all the atom in line and then measure the length. So there's always this kind of issue that your mathematical description of the system can be closer to actual system. However, it's not always perfectly lined up. And there's always uncertainty. Actually, this uncertainty will lead us to a subfield of the control, robust control. And in robust control, we will investigate which point does the controller fail and so on. However, that's way beyond the scope of this course, so we're going to talk about that in another time. Anyway, the point here I wanted to make is that these steps are not trivial steps. And then you have to go through all this iteration. So to begin with, we're going to take a sort of a shortcut to test this. First, we're just going to implement and then see how the system behaves, and then come back to the implementation and then design the controller or tune the gain again, and then try, fail, test, and so on. Actually, as this is a shortcut, and this is very popular in industry, and a lot of open source projects such as PX4 is relying on this method. And this is really powerful and very quick. If you are lucky, you can just launch your product as soon as possible. Another type of shortcut to make your system work is to reading the research papers, because it is the researcher's job to publish a new controller and new design strategy for a system. So oftentimes these researchers publish their paper and share their ideas with the community. Well, although you may not be able to find exact system that you want to control, but still, if you can find a similar system, it could be a very good starting point. So that was the brief and high-level overview about the workflow in control field. And the reason why I wanted to show you this kind of workflow diagram is, in general, if you happen to land on a new job, you should be able to schedule your work, like by assessing the stage of your project, make conclusion about what you need and where to start, what could be your next step, and so on. Also, for a studying purpose, you should be able to determine what to study more, where to deep dive, and so on. That's why I'm showing you this diagram. So I wish this diagram could be a kind of a good starting point or a map so that you can later find where you are at and so on. Although this may not be precise depiction about the process in general, but I'm pretty sure this will be a good starting point for you. So in the later chapter, we're going to talk about first the shortcut, this one in chapter 2, And before we begin this full workflow, I'm going to talk about a simple math. And then in chapter 4, I'm going to talk about the transfer function method from yellow to white, and do the same in the later chapter using state space method. Before moving on to the next chapter, let's see how we can download the course material. Simply, on the right top there, you can click this file button, then click this so you can download the zip file. Or simply you can click this yellow button, then you can also download file like this. If you have followed the instructions from the welcome course, how to prepare all this environment for this school, you should have this work environment folder, and then underneath the workspace, unzip the file, then you should be able to see these files.